right here is our volume. So that makes our conversion from molarity to moles very simple. 2 moles of this, 0.1 mole of this. And we also have some of the NO2 already. We have 2 moles of that. Water's not going to matter anyway. We really only care about this one and that one, unless one of these runs out. So the limiting reagent in this case is the hydroxide ion. That's going to run out. It's going to go to 0. So when that does that, that's going to go from 2 down to 1.9 moles. And the 2 moles here, because the reaction shifted to the right, the amount of products goes up by the amount that those went down. So our amounts of the acid and the conjugate base have changed. They're still close to what they were before, so that means the pH is not going to change very much. That's kind of the idea of a buffer. The more concentrated your buffer components are, the more they can withstand reacting with strong acid or base. But now from this point, we need to take those amounts of the acid and its conjugate base and rewrite that same equation. I'm going to take you back here. This equation that we used to figure out the pH in the first place, we go back to it now that the concentrations have changed. Because we still need to figure out what the new hydrogen concentration is. Because our amounts of this and this are not the same anymore. So when you do an ice table using the K, you have to use the unit molarity. Don't forget about that part. So with the stoichiometry, you use moles, but then as soon as you're done with the stoichiometry, you know the final amounts of those. Then you plug it in as molarity to the equilibrium part. So let's see. The fact that our volume is 1 liter makes this nice. The NaOH didn't affect the volume of it. So the HNO2 is 1.9 molarity, and that is 2.1, because they're both being divided by 1 liter, which was handy. So this has to shift to the right. It's going to be 1.9 minus x, and 2.1 plus x as this thing shifts to the right. And that's what we'll put into our K expression. 4 times 10 to the negative 4th equals the products, x times 2.1 plus x over 1.9 minus x. And those plus and minus x terms are neglected. And once again, knowing where we've come from using the quadratic formula, this is pretty doable. You don't have an x squared term, you just have an x. So the K gets multiplied by 1.9 and divided by 2.1. What is the pH? 3.44. Everybody get 3.44? We have to practice this a lot. I warned you, writing the chemical equations is the worst part of this. So knowing what to do when you have something that's added to a buffer, even what you do when you just have a buffer, just takes some practice. We have to do it a lot, practice, see what the solution guide says. You're welcome to ask me anytime. We'll get there. Okay. Now this is going to be a shortcut that's going to make our lives much easier. I really like teaching the buffer equation because it is going to just simplify all of our problems involving buffers. And simple sounds pretty good. So I have a relationship up here. I just want to write up on the board how I got it. It's not going to be a big surprise to you, but I think it's important to know where that came from. So if we have an acid, a weak acid, that's dissociating into hydrogen ions and the conjugate base, the Ka of that acid is products over reactant. That's no big surprise. Solve this thing then for the hydrogen ion. Just get hydrogen by itself. That is how I got this. We take the Ka, we need to get hydrogen by itself, so you got to move the A minus and HA over to the other side. So I had the Ka, and I wrote it like this. You'll see why in a second. Ka times HA divided by A minus. That's what we have. Okay? There's a reason that I took this. I mean, we're used to this, the Ka expression. We're very comfortable with that. We've been at it for a long time. Why did I solve it for H plus? Here's why. Because if we take the negative log of both sides of that equation, okay, so when you hear negative log, something probably pops up in your head, right? And what did we just solve for over here? H plus. So negative log of H plus. Oh yeah, that sounds familiar, doesn't it? So negative log of both sides, which means if I've got to take the negative log of this side, I need to also take the negative log of that side. And you know that when you take the log of two things being multiplied by each other, it would be the log of that plus the log of that. Yes? We've done some logs. I think some of us have. So this is what it would look like. The negative log of H plus on the left equals the negative log of the Ka plus the negative log of that ratio. There was two guys that came up with this buffer equation. One, I believe, was German, and the other one, I think, was Scandinavian, like Swedish. Their names were Henderson and Hasselbalch. So this is always known as the Henderson-Hasselbalch equation, aka buffer equation. Okay, now here I'm boasting that this is going to make our lives so much easier. What's happening right now? Well, let's get the new name of these things. What is another name for negative log of H plus? That's the pH, right. So this is a way of finding the pH of something. How do we do it? Well, the pH is equal to, this one we haven't seen before, but I think we could maybe come up with a name of it. What do you want to call the negative log of the Ka? If negative log of hydrogen ion is pH, how about negative log of Ka? pKa. It's fine. pKa. In fact, on our last quiz in chapter 14, I accidentally put the pKa of an acid. It was on number 5. You remember me doing that? And I said, shoot, I wasn't thinking when I put that, so I had to write the Ka value because, yeah, we hadn't learned what pKa was. And now you'd be able to do that. It would be no problem. All right, now this part right here, we can't simplify because these amounts vary. It depends on what happens in the buffer. The acid and conjugate base concentrations are going to change. However, there is one thing about this. This sign is negative. This means plus negative 1 times the log of that ratio. Do you remember what you can do when you have something multiplied by the log? Right. I see what you're doing with your hand. You're doing this. That negative 1 goes up here as a what do I want to say? Exponent. It's an exponent. So what would that be? If HA over A minus was raised to the negative 1 power, would you agree that that just flips it? It inverts it. So this is the same as plus log of A minus over HA. That's what we have here. This is our Henderson-Hasselbalch equation. You can use this instead of that second step. Now, if I can just take you back we got the number of moles of our acid and conjugate base, you can take those amounts and go right to the buffer equation and apply that. And it's so much faster to get the pH. It's easy to use. Not too often do people get it wrong, especially with our fancy calculators that we use. It's very nice. Now, one other thing I want to say about this buffer equation is that, you got a question, John?
Yeah, I was just going to ask now, we just split that way.
I don't think that I can remember any examples of when you have a diprotic in which we're not just using the acid and its conjugate base. For instance, H2CO3 is diprotic, carbonic acid. Its conjugate base is HCO3. CO3 with a -2 is not the conjugate base of H2CO3. So I think we're always just differing by one hydrogen. I'm not thinking of any time where you're ever going to see anything different than just one hydrogen different. It's good you're thinking. I like that. But check this out. This is going to make your math even easier. You see how I have the log of the ratio of the concentrations? See, I got the molarity brackets in there. This is the buffer components, the acid and its conjugate base. They're in the same solution. They have the same volume. So remember, molarity is moles per liter. The liter of this and the liter of that are the same. So not only do you have the ratio of the molarities, it's also the mole ratio in the solution. So where in the last problem, when I got to this, moles of the acid and moles of the conjugate base, that's the exact same as the ratio of the molarities. So just use moles for that ratio in the buffer equation, and it'll work. It'll give you the exact same answer as if you use molarity. Now, the one thing that I would mention about this, as you know, I don't trust my memory. I'm always concerned that, gosh, if I commit something to memory, when the pressure's on and I'm feeling nervous, will I remember it right? pH equals pKa plus log of, is it base over acid or acid over base? I can't remember. And then I panic. Here's how I remember this one. Because this makes our our work so easy, I think of this equation as, bah, it's so easy. And so when I think, bah, B over A, and I always remember. In fact, every time I recite this, and you'll hear over the next several days when we use this all the time, I call it pH equals pKa plus log of bah. And so we got it. Now you won't forget it. And this pKa, you know, in a buffer you always have acid and base. Even if you're given the Kb of the base, you need to plug in the Ka of the acid. This is required. You know, like 3 slides ago, we were dealing with this. I gave you the Kb of ammonia. When you use the buffer equation, you got to have the Ka. So, and we'll see that I think in our last example. I just got some things in the next 2 slides. I'm going to skip over that for a second. Let's try this problem using the buffer equation. Now we still always have to do the stoichiometry step to find out what the new concentrations of the weak acid and conjugate base are. So you got the stoichiometry step, then apply the buffer equation. We're going back now to our ammonia-ammonium buffer. .3 liters of strong acid are added. We got that vicious dog that attacks the solution. Would you be able to write the chemical equation for how the buffer responds? And when you just write your chemical equation, show somebody around you. Make sure you both have the same chemical equation.